This is a walkthrough of the AS Further Mathematics paper, and this is AS FM1 or Further Mechanics 1. Question 1. A ball is projected with speed 6 meters per second up a line of greatest slope of an inclined plane. The plane is inclined to the horizontal at an angle alpha, where sine alpha is 1/7. The ball is modelled as a particle, the plane is modelled as being smooth, and air resistance is modelled as being negligible. That means it's so small that we can ignore it. Using the conservation of energy principle, find the speed of the ball at the instant when it has travelled a distance of 5 meters up the plane. So let me highlight what I want. So let's underline that. Initial speed 6, the angle of incline is alpha, and sine alpha is 1/7. The plane is modelled as being smooth, and basically we're ignoring air resistance. We need to use the conservation of energy principle, so this means not SUVAT, and we want to find the speed of the ball in the instant when it has travelled 5 meters up the plane. Okay, right, so the first thing I'm going to do is to draw a diagram to show everything that's going on. So here's my inclined smooth plane at an angle of alpha, and I've been told that sine alpha is 1/7. Now what we don't do is do the sine inverse of 1/7 to find the angle. We don't need to. You'll see as we go through the working. And my particle starts at a point down here, moving at a speed of 6 meters per second. It then moves 5 meters up the slope, so let's put 5 meters here as the distance that it's moved up, and we need to work out what speed it is at that instant, so we'll call that V. Now, because we're using the conservation of energy principle, and since no energy is lost by work done against friction, then the energy at the start is equal to the energy at the end. And what I mean by start is here at the bottom, and what I mean by end is the end up here. So let's work out the energy at the start. Now that energy is going to be made up of potential energy and kinetic energy. So what I'm going to do is call the bottom of the slope the point of zero kinetic energy, or sorry, zero potential energy. So at the start, potential energy is 0. Kinetic energy, half mv squared, is half. Now the mass of the particle, we're not given, so we'll just call that m. So half m, and then v squared, 6 squared. Okay, so the total energy I have at the start is half m times by 6 squared, or half m times by 36. In other words, 18m. Okay, let's look at the energy at the end. Again, we'll look at potential energy and kinetic energy. Now for potential energy, the particle has moved up the slope. We want to work out the vertical distance that it's moved up the slope, which I'm going to call h. So basically what I've got here is a right angle triangle where this angle is alpha, the hypotenuse is 5, and I want to find this length here. So the height at which it's moved up is equal to 5 sine alpha. So if we want to work out the potential energy, it's going to be mg times by the height. Vertical height is moved up, so that's going to be times 5 sine alpha. So this is where, when we go on to the next point, we would replace that sine alpha with 1/7. So you see, we don't need to know what the angle is. Next, after that, we'll work out how much kinetic energy there is, and that's going to be half m. Now it's v squared, because the speed we want to find is v, or whatever letter you've used for your unknown, so half mv squared. So the total energy at the end is going to be half mv squared plus mg times by 5 sine alpha, or 5 times by 1/7. So my conservation of energy equation is going to be half mv v squared plus, and then if I work this out here, I'll basically have 5 over 7 mg. 5 over 7 mg is equal to 18m, and I need to find v. So the first thing I can do is cancel out all the m's, leaving me with half v squared is equal to, I'll move the 5 over 7g over, so I've got 18 minus 5 over 7g, times both sides by 2, so I'll get v squared is equal to 36 minus 10 over 7g. So let's put that on our calculators and work out what v squared is equal to. That's exactly 22. So v is going to be equal to the square root of 22. Now, since we have used g in our working, do not write the exact value or lots and lots of decimals. Answer should be rounded to 2 or 3 significant figures anytime we use g. I'm just going to be consistent and always use 3 significant figures unless I'm told otherwise. So if I were to write down what I fully get on my calculator display, that is 4.6904 and so on. So I'm going to give v is equal to 4.69 to 3 significant figures. Now you could also give an answer of 4.7, and that would be 2 significant figures. So the only time you can do 2 significant figures is when you're using g, or whether you're asked to give an answer to 2 significant figures. Otherwise, always do 3 significant figures. Question 2. A particle P of mass m is moving in a straight line on a rough horizontal table. The particle collides with a fixed vertical wall. Immediately before P collides with the wall, P is moving with speed u in a direction which is perpendicular to the wall. In the collision, P receives an impulse of magnitude 5 mu over 3. After the collision, the total resistance to motion of P is modelled as a constant force of magnitude 5 mg. Part A, find in terms of u and g the distance of P from the wall when P comes to rest. So I'm just going to underline the important bits of information here. So the mass of the particle is m. It's on a rough horizontal table, so there's going to be a frictional force. It collides with this vertical wall. Before it collides with the wall, it's moving with speed u. It receives an impulse of 5 mu over 3, and the total resistance to motion is modelled as a constant force of magnitude mg over 6. So the first thing I'm going to do is to draw a diagram. So I'll draw my wall here like this. This is how I always draw my walls. I'll draw my particle P here of mass m moving towards the wall at a speed of u and away from the wall. Well, we'll call that speed v. We're not told what it is, so I'll just call it v. And then there's an impulse which the wall gives the ball, and its magnitude or size is 5 mu over 3. And then when the particle's moving away from the wall, there's this constant resistance. So if it's as the ball is moving away, the resistance is going to act towards the wall, so it's going to be acting in this direction here. So this is my resistance here, resistive force, and that is mg over 6. So let's start writing some equations down. So I'll start with my impulse equation. Now I'm going to take moving away from the wall on my diagram to the left as positive. An impulse is equal to mv minus u. So the impulse we're given as 5 mu over 3, and that's going to equal the mass, which is m, and then v, which is v, that's going in my positive direction, and then I need to subtract. Now u's going in the opposite direction to my positive, so it's v minus negative u. Let's now simplify that. So you've got 5 mu over 3 is equal to mv plus mu. We can cancel out the m's from all of the terms, and if I rearrange it to, let's rearrange it to make v the subject. I will have 5u over 3 minus u, so v is equal to 2u over 3. Now the reason I've found the speed here as it goes away from the wall, because I'm going to be using F equals ma and suvat to work out the distance it goes before it comes to rest, and this 2u over 3 is basically going to represent u in my suvat, basically the initial speed as it rebounds from the wall. So let's find now the acceleration or deceleration as it moves away from the wall. So again, I'm taking to my left as positive. So the only forces acting on the particle is this resistive force acting in the opposite direction to motion, which is mg over 6. So that's going to be a force of negative mg over 6 is equal to ma. I want to know what the acceleration is, so I can cancel out m's from both sides, and that will give me the acceleration as negative g over 6, basically a deceleration as g over 6. Right, so I have a initial velocity u, I have an acceleration, and I know that the final velocity when it comes to rest means that I'm going to be taking v equal to 0. So let's write out suvat, s-u-v-a-t. So I want to find the distance. U is 2u over 3, v is 0, it comes to rest, and a is negative g over 6. So that means I'm going to be using v squared equals u squared plus 2as. Substituting the values in, I will get 0 squared is equal to 2u over 3 all squared plus 2a, that's negative g over 6, and then s is what we need to find. Rearranging for s, I will have negative 2u over 3 all squared over 2 times by negative g over 6. That's a g there, not a 9. Let's see what we get for s. And that simplifies to 4u squared over 3g. So I've got the distance, and this is in meters, in terms of u and g, which is what they wanted. So we can't get a numerical answer because we don't know what the exact value of u is, but there we go. Part B. State how the model for the total resistance could be refined to make it more realistic. Now, if we look back at what we're given in the question, you'll see here that the total resistance is modelled as a constant force, and this is the key here, this word constant force. So there's the clue to our answer. Now, in reality, resistive forces aren't constant. They change with velocity. As something speeds up, normally the resistive force increases in some sort of proportion to that. So I would write down, and we only need to state something. We don't need to say why, it just says state. So we could use a variable resistance, which is dependent on speed. Question 3. A car of mass 500 kg is moving at a speed v meters per second. The total non-gravitational resistance to the motion of the car is modelled as having magnitude 5v plus c newtons, where c is a constant. The car moves up a straight road which is inclined to the horizontal at an angle theta, where sine theta is equal to 1 over 14. When the engine of the car is working at a constant rate of 25 kilowatts, the car is moving up the road at a constant speed of 20 meters per second. Part A, what we need to do is find a value of C. So let's underline what we've got. So we've got the mass of the car. It's moving at a constant speed of V. The non-gravitational resistance is a size of 5V plus C. So this is different to the previous one where it's not a constant resistance, it is dependent on the velocity. C is a constant. It's moving up the road at an angle of theta, and we've got sine theta is 1 over 14. So again, on this question, we are not going to work out the angle. We're going to use the exact value of sine theta in our working. We're told that the engine's working at a rate of 25 kilowatts and moving up the road at a constant speed of 20 meters per second. Okay, so let's start with our diagram. So here's my incline road, and an angle of theta, I'm just told sine theta is 1 over 14. Here's my car of mass 500 kg, and its engine, its tractive force here is equal to P over V. So remember that if we do the force times velocity, that is equal to the power. So basically that's what I've used over here. And then there's a resistive force, which is 5V plus C. Now we'll need to include the gravitational forces. So the weight is 500G. And then on these types of questions, like, you know, we've got a component here and a component here. We are only interested in the component which is parallel to the slope or the road, and that's going to be 500G sine theta. And lastly, we'll put on the velocity that it's moving at, and that's 20. Now, because it's moving at a constant speed, that means that the forces going up and down the slope are balanced, or the resultant force is going to be 0. So that's going to help me form my equation. So basically the pulling force, P over V, the tractive force, is equal to the sum of the resistive forces. So that's going to be the 5V plus C and the 500G sine theta. Okay, so what I can do is now put some values in. P is 25 kilowatts. So remember, kilowatt is 1,000 watts. So it's 25,000 over the velocity, which is 20, is equal to 5 times by 20. So I'm looking at this bit here. So 5 times by 20 plus C, and then plus 500G, so that's 9.8, times by sine theta, and sine theta is 1 over 14. So you see, we don't need to know the angle. I'm going to rearrange this for C, and I'll get C is equal to 25,000 over 20 minus 500 times by 9.8 times 1 over 14 minus 5 times 20. Now if we work all of that out, I get exactly 800. So the value of C is exactly 800. Part B. With the engine of the car again working at 25 kilowatts, the car now moves along a straight horizontal road at a constant speed of u meters per second. Find a value of u given your answer to two significant figures. So we have the same power as before. it's moving at a constant speed of u. So let me do a diagram for this question. So here's my horizontal road, here's my car here, same mass, 500 kg. Its tractive force is P over V, the velocity that it's travelling at. Its resistive force, now remember that is 5V plus C, we've worked out C, so that's going to be 5V plus 800, and we're told that it's moving at a velocity of u. So just like before, these forces are going to be balanced, or the sum of the resultant forces is 0. So let's start by writing our equation. So the tractive force is P over V, which is actually u, that's the velocity it's travelling at, is equal to 5u, that's the speed, we replaced the V with all the V's with u, plus 800. Now we know that the power is 25 kilowatts over u, and then we'll rearrange it, minus 5u minus 800 is equal to 0. So the way that we need to solve this, if we times everything by u, we're going to get a quadratic, which we can solve using our calculator, and that will give us minus 5u squared, if I put everything in order, minus 800u plus 25,000, or I can flip all the signs around, is equal to 0. So using our calculator, we'll solve that. We'll get two solutions. I think one is negative, we ignore the negative, but we'll get u is equal to 26.7707 and so on. It does say that we need to give our answer to two significant figures, so that will be an answer of 27. So u is equal to 27 meters per second, so that's our value of u. Question 4. A particle P of mass m is at rest on smooth horizontal ground between two fixed parallel vertical walls. Another particle Q of mass m is moving in a straight line along the ground between the walls in a direction which is perpendicular to the walls. Particle Q collides with particle P directly. The coefficient of restitution between the particles is e, and the speed of Q immediately before the collision is u. Part A. Show that the speed of P immediately after collision is u over 2, 1 plus e. So the first thing I do, and which I would do on pretty much all mechanics questions, is to draw a diagram. So first of all, I'm going to draw my two walls which are parallel to each other. Between them I have P and Q, my two particles here, so P and Q. They both have mass m. Before the collision we have P moving towards Q at speed u, and P is at rest. The coefficient of restitution between them is e, and I want to find the velocity of P after the collision, so I'll call these velocities v and w. So the first thing I'm going to start with is the conservation of linear momentum. I'm taking to the left as positive since everything's moving that way, so that will give me mu, that's the only momentum before the collision because P isn't moving, is equal to mv plus mw. I can cancel out all the m's and I get u is equal to v plus w. Next I'm going to use my coefficient of restitution, so v is equal to eu, so v is the speed of separation. I've got v in front of w, so that's got to be going faster than w, so speed of separation v minus w is equal to e times the speed of approach, and that's just u because P is at rest. Okay, and then what I want to do, because I want to find the speed of P, in my working here, the speed of P is going to be v. So I want an equation for v, which means I need to eliminate w, and I can do that by taking this equation here. Let's highlight this equation. So these are the two equations I'm going to use, and rearranging this to make w the subject, so I can eliminate w from my equation, and that'll be w is equal to u minus v. So now let's substitute it into here, and so v minus, and then in brackets w, which is u minus v, is equal to eu. That will give me 2v minus u is equal to eu. Add u to both sides, 2v is equal to eu plus u. And then what I can do from here is make v the subject, divide both sides by 2, and also factor out the u, because I'm looking at what I've got here. So u over 2, and then in brackets I will have 1 plus e. So always leave your answer in the form that they ask for. So I'll put that as required. Part B, find the speed of Q immediately after the collision. Now the speed of Q is what I've called W in my working. So I'm going to use this same equation here, but I want to eliminate V from my coefficient restitution equation. So if I start with my U is equal to V plus W, rearrange it to make V the subject, and V is going to equal U minus W. I'll substitute this into here, so it'll be V, which is U minus W is equal to EU. So I've got U minus 2W is equal to EU. That will be 2W is equal to U minus EU. We're pretty much there. Divide both sides by 2, factor out the U, and I'll write it in the same form as I did as it was given in this one here. So that would be U over 2, and the 1 minus E. So very similar to the last one, except that this is going to be 1 minus C instead of 1 plus C. Part C. Given that the total kinetic energy lost in the collision between the two particles is 3mu squared over 16, find the value of E. Right, so we know that the kinetic energy lost is going to be equal to the kinetic energy before the collision minus any kinetic energy after the collision. So before the collision it is just half mu squared, and then I subtract from that the sum of the kinetic energy after the collision. So that's going to be the kinetic energy from P and U. So half m. Now if I look at this is going to be like my V basically. So I'll need to square that. So I'll put that in brackets. So that'll be U over 2 and then 1 plus E, and that's all squared, so half mv squared, plus the other kinetic energy is going to come from Q. So this will be like the same sort of thing, so half m, and then the V is going to be this U over 2 1 minus E. So U over 2 1 minus E, and that's all squared. Now let's try and simplify this a bit before I start expanding brackets and doing things like that. So let's think about each bracket that's squared. So if I square the whole bracket, I'm going to get U squared over 4, and then the squared is going to be there. So the stuff I'm writing in red basically is what's going to happen to that squared, and this will be U squared over 4, and again it'll be 1 minus E all squared. Now every term now has got half mu squared. So I've got half mu squared here, half mu squared here, and then half mu squared here. So if I factor out the half mu squared, I will have that outside the brackets, half mu squared, and then in the brackets it'll be 1 minus a quarter 1 plus e all squared minus a quarter 1 minus e all squared. And then what I'll do from here is I'll expand the brackets of the 1 plus e squared and the 1 minus e squared. So still have the 1 half mu squared outside. Then inside the brackets it'll be 1 minus a quarter of 1 plus 2e plus e squared. From the first one expanded, and then minus another quarter and 1 minus 2e plus e squared. Now the quarter 2e and the minus quarter 2e, they're going to cancel out, so I'll just cross those out. Now from here this will simplify to, let's get the right colour, half mu squared, and then what we have in the bracket will basically become 1 minus a quarter, so that's a half, and then we've got negative a quarter e squared minus another negative a quarter e squared, so minus a half e squared. So what we'll do is we'll take the half out. That means that I'll write this fraction in front as a quarter, and then that means in the brackets it'll just be 1 minus e squared. So 1 minus e squared, like this. Now at this point I'll write down what it's equal to. So that's 3mu squared over 16. So I'm just going to sort of, as I do the work and I'll rub it out, I'll times both sides by 16. So 16 times a quarter, so that means I'll get 4 on this side, and then I can get rid of the divide by 16, so that'll be 3mu squared. I'll divide both sides by mu squared, okay, so I can just rub that out. So that just leaves me with 4, and then 1 minus e squared is equal to 3. I'll divide both sides by 4, so that just leaves 1 minus e squared. 1 minus e squared is equal to 3/4. Then from there, what I'll have is e squared is equal to a quarter. Square root it, e has to be positive, so that means e is equal to a half. So there we go, finally got there. That is the value of e. Now I need to rub out that bracket because it looks like it's minus a half, and just make that bracket a little bit smaller there, like that. Okay, part D. Suppose now that the coefficient of restitution between the particles is 1 and the coefficient of restitution between each particle and each wall is 1. By considering at least 2 collisions between the particles, describe in detail what happens in the subsequent motion, giving reasons for your answers. So I'm going to start with the first collision and then 2 subsequent collisions. That's going to be the second and the third collision. Okay, so this is basically a setup of the first collision where Q has a velocity of u, P is at rest. Now if we're told that E is equal to 1, we can now work out the velocity of P and the velocity of Q. So the velocity of P, now what's going to happen here, we'll have 1 plus 1, which is 2, u over 2 times 2. Its velocity is going to be u, and then the velocity of Q, again, E is equal to 1, so 1 minus 1, 0. So the velocity of Q is equal to 0. So this is the setup for the second collision. P is moving towards the wall at speed u, and it's going to rebound from the wall. Now if we use V is equal to EU to work out the speed of P after it rebounds from the wall, since E is 1, so V is equal to 1 times U, so that's just going to be U. So it's going to rebound at the same speed that it hit the wall, which is U. Now this is the setup of the third collision. So P rebounds at a speed of U towards U, which is at rest. That was the at rest part here. And then again, working out V is equal to EU, then P will now be at rest and Q will move off with speed U. So in the third collision, I could sort of say that it will be the same, and I'll put that in quotes because it's not exactly the same, but the velocities are the same. What's happening is the same. One particle moves off at the same speed as the other one was moving towards it, and then the particle that was moving comes to rest. So it will be the same as the first collision, as the velocity of P will end up as 0, and then the velocity of Q will end up as U. So you can see I've got the same type of thing as I had here, but like the opposite way around, and then Q will hit the other parallel wall at U, rebound at U, and then we're back to like this first collision, this first setup again. So I've put here, I've tried to explain, I don't know if I've done it particularly well. In the continuing the motion, Q will rebound off the wall at speed U, so I'll put and speed U, that should be at speed U, and repeat the process. In other words, these previous 3 steps. There's almost like 4 steps. P at rest, Q moving towards U, and then Q being at rest, P moving off at U. So that's like the first step. Second step, P moves towards the left-hand vertical wall on my diagram, left-hand vertical wall, moves towards it at U, rebounds from U. Third step, P then moves back towards Q at U, then that collision will bring P to rest and Q moves off with U, and then Q is going to hit the other wall at this end at U and then rebound at U, and then we're back to this step. Yeah, so it's just going to repeat in this endless cycle.